I was going through some information on electrobiology, and
Managing your diabetes just got easier.
I came across the NGF protein, which is the nerve growth factor, and we're gonna take a look at the video right now. We're gonna skip all the front because it's just them giving shout outs to all the organizations that made this possible, this research possible. So it says that when a sympathetic or sensory ganglion from a chick embryo is cultured, its cells produce a halo of nerve fibers. So here we have a nerve. As we can see, that's 1 day of time. A protein, nerve growth factor, stimulates outgrowth from a ganglion. In the absence of NGF, outgrowth is minimal. Now, if you take a look at the NGF, the protein, look at the bottom. You see electricity. You see electrointeractivity, helping form everything. You see the electricity, the little light, it literally moves around. If you look real good all the way around, you'll see that the nerves are actually extending with the help of these like little electrical bursts. That's 2 days. Nerve fibers grow out of dissociated ganglion cells cultured with NGF. A network of fibers is formed. These are nerve fibers. We could see them extending, organizing, intelligence all the way around. You see this. You see the intelligence, what they're doing. They're working together, and throughout the whole time, you see those little electrical bursts. That is clearly intelligence. It's not random. Okay, let's pause right there. Let's go out. Okay. So going back. So I was like, okay, well, what's a protein then, right? We hear all that talk about protein over and over, especially because of this whole pandemic that happened, or scamdemic, or whatever you guys want to call it. So what are proteins and what do they do? Proteins are large, complex molecules that play many critical roles in the body. What do most of the cells they do most of the work in cells and are required for structure, function, and regulation of the body's tissues and organs. Okay, so then you just simply look up molecules next. A molecule is a group of atoms bonded together representing the smallest fundamental unit of a chemical compound. And this is where everything gets crazy and weird. Because when you look up an atom, atoms are a source of nuclear energy. It's the basic unit of a chemical element. Okay, so it's a particle, it's a unit, it's a molecule. So you're like, okay, well then let's see this stuff. Let's in the molecule we've already seen this atom. They keep going in circles, right? So then we'll move up here to chemistry.hall. And can we see real atoms and molecules? Electron microscopy at a glance. A universal challenge that has been keeping chemists busy ever since the modern concepts of atom and molecules were conceived is how to actually characterize molecular compounds, either human made or found on nature. But can we see real atoms and molecules? Confirming the actual structure of a molecule is still a big challenge nowadays. The advances in techniques such as nuclear magnetic resonance spectroscopy or single crystal X-ray diffraction have significantly helped speeding up this problem. Molecular structure determination. Every month we get reports of chemical structures whose structures have to be reassigned or revised after some study, either synthetic or just based on characterization techniques, is carried out. On this regard, it is worth remarking the difference between scientific models and reality. The complex chemical structure of myotoxin, you can see right there what it looks like according to what they believe right now. That scientific model, as we're seeing, of myotoxin can change. Truth is, even today, the methods for the characterization of molecules available to use routinely, which are explained in the most basic chemical bibliography, can be considered rather rudimentary and of difficult interpretation for non-experts. Let me be honest. I am a trained PhD organic chemist, and if I had to take a look at the NMR spectra of a complex natural product such as myotoxin, I would probably have no clue what I am looking at. Single crystal X-ray diffraction is probably the closest method to easily visualize the structure of a molecule in 3D. However, this is not a bulletproof method. The sample preparation, growing single crystals, required for this indirect technique renders it useless for a wide variety of chemical compounds. Can we actually see real molecules or atoms? I would say that by today, there should already be a method that allows taking a direct microscopic picture of any compound you like and immediately visualizing its structure in a screen. Apparently, we are not quite there yet in regards to any compound. Keep reading. However, the answer may come under the name atomic microscopy and all of its variations. Atomic force microscopy, AFM, or scanning force microscopy, SFM, is a very high-resolution probe microscopy technique. It allows us to actually see or take real pictures at the nanometer scale in which the molecular realm lies. A picture is worth 1,000 words. In the example below, scientists make use of this technique to get pictures of a compound called naphthalene tetracarboxylic diamide. We can actually see a real molecule. Credit to P. Mortuardi co-workers mapping forest green hydrogen bottom. So, seeing atoms in motion. The world of visualizing at the atomic level took leap more than 10 years ago. In 2008, a research group recorded The world of visualizing at the atomic level took a leap more than 10 years ago. In 2008, a research group reported the imaging for the first time of light atoms and molecules on graphene. Subsequently, the same team managed to observe for the first time the actual movement of insulated graphene atoms in real time. The following movie from the Berkeley team shows the growth of a hole in a graphene sheet. For this experiment, a beam of electrons is focused to a specific spot on the graphene sheet, blowing out the focused carbon atoms, making a hole. Besides, it can also be observed how the carbon atoms rearrange themselves, edge reconstruction to adapt more stable configuration. You see what the credit goes to? You guys can look that up. The Boy and His Atom, the world's smallest movie. The Guinness World Record of the smallest stop-motion film is held by a movie recorded by IBM scientists. Sometimes nanophysicists also need to have a bit of fun, and what they decided is to film a movie by using scanning tunneling microscopy. As a result is in the following video, and you see the video right there. We can take a look at that right now. By use of this technique, the scientists managed to move a lot of molecules of carbon dioxide following their will. The result is a movie you can only see using a microscope that magnifies 100 million times. Okay, so obviously taking real pictures of a molecule and atoms was just not enough for the scientific community. If we fast forward to the year 2013, atomic microscopy, more specifically non-contact atomic force microscopy, allowed the direct imaging of molecular structures during a chemical reaction. So some results of these experiments published in the journal Science are displayed below. We cannot only see the actual atoms, molecules, we can observe direct chemical reactions. So what you're actually seeing is the reactions, which is definitely electrical. AFM and structural determination. This field started as a cluster of isolated cases, but as the years went by, more and more examples of this application of this set of physical techniques are being constantly reported. The level at which the study molecules can be observed is rather impressive. A recent example is the actual structural determination of a natural compound, Brightufficin A. Brightufficin, whatever. Several functional groups of the molecule were derived from classical spectroscopic data. Then an AFM image, allowed observing the real structure of the molecule, placing each piece of the puzzle in the correct spot. This has established the previously unknown structure of the molecule. So you can see how they just look at stuff and then they try to outline it. Taking real pictures of complex chemical reactions. On the reactivity side of things, much more recently, it was possible to directly image the course of a reaction called the Bergman cyclization. This is one of the most fascinating rearrangements in chemistry. The chemical transformation is directly induced in the metal surface in which the atomic microscopy procedure can be carried out. Excuse me. As you can see, how they use the imagery to draw out these little outlines. However, as stated at the end of the introduction, not every molecule or reaction can be a candidate for a STM study as these. Several conditions need to be met. One of them, which might have already called your attention, is the analyzed compounds need to be near planar. These techniques rely on depositing the molecules of the compound in a planar metal surface. So planar molecules are the ones that give more interpretable data. Okay? The electrointeractive plane of existence. Do you guys even science, bro?